Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been dealing with various pulse width modulation methods for power electronic converters. So, we are particularly looking at this DC AC converters and many modulation schemes like sine triangle or space vector and such kind of PWM methods, and how you would analyze the harmonic the waveform quality in such cases and so on and so forth. So, this course has had so many modules till now, a few more modules are yet to come, 4 more to be precise. So, the initial module, many of you might have seen a part of this or maybe completely. So, this has got an overview of power electronic converters where we discuss the various topologies, DC-DC converters and DC-AC converters, voltage source and current source and multi-level and flying capacitor and so on. Then we looked at a few applications of voltage source converters like motor drive and reactive power compensation and so on and so forth. Then we looked at some fundamentals of pulse width modulation. Then we looked at how to generate pulse width modulation at low switching frequency. Sometimes when the inverter operates at a very low switching frequency, how would you generate the PWM waveforms, and we looked at some studies on that. So, we looked at things like selective harmonic elimination for this purpose. And interestingly, today we will be doing something very similar to that in this part of that. So, in the last lecture we actually discussed on some low switching frequency PWM method, and we were trying to look at the pulsating torque produced by inverters, I mean the motor drives, which are fed by inverters that switch at low frequency. So, today we will be dealing with it a little bit of it again, and then these are the high frequency PWM methods. That is when the switching frequency is much higher than the modulation frequency, the fundamental frequency. Let us say fundamental frequency is 50 hertz, but the switching frequency is a few kilohertz. So, in such kind of cases you use this triangle comparison method or the space vector based PWM method. So, in triangle comparison you have things like sine triangle PWM, third harmonic injection, etc. In continuous and discontinuous PWM methods. So, in space vector you would normally use conventional space vector, and you would use bus clamping PWM methods. So, all these methods, as I mentioned before, can be implemented either using a carrier comparison approach. That is, you can have 3-phase carrier waves and compare them with 3-phase modulating waves and compare them with carrier and produce the PWM waveforms, or you can use the space vector approach where the reference is provided as 3-phase revolving a revolving voltage vector, and this voltage vector is sampled and you try to apply that, apply voltage vectors and use the time averaging of different voltage vectors produced by the inverter to synthesize that. As I mentioned on a number of occasions, there are some space vector based PWM schemes which cannot be implemented based on triangle comparison approach. That is, space vector based PWM can do little more than what triangle comparison can do. So, those we call them as advanced bus clamping PWM methods in this course, and so we have also discussed some of those methods earlier, and today we will be looking at them again briefly in the context of pulsating torque ripple. So, we would be looking at somewhat on these things, and particularly with an emphasis on higher switching frequency today in the context of torque ripple. That is, after we did the high frequency PWM, we did the analysis of line current ripple. In some sense there is some similarity between the analysis of line current ripple and the torque current ripple, like we would see today. Alright. So, as I mentioned, so the last lecture our focus was on low switching frequency. Now, it would be a review on the low switching frequency. So, like quick recap on low switching frequency PWM and the voltage, current and flux harmonics, and revolving magnetic fields produced by the fundamental and harmonic voltages, and steady torque produced by fundamental components, and the pulsating torque produced by the rest, mostly by the interaction of one fundamental magnetic field and another harmonic magnetic field. And then we looked at selective elimination of harmonic tech. We looked at it towards the end of the last lecture. So, we would look at this once again today, and then we would move on to what is really the focus for today, that is the high switching frequency PWM. So, we will look at it from the space vector point of view, because that is what is more general than the triangle comparison, and we will be dealing with certain space vector based PWM methods which really cannot be implemented from the triangle comparison mode, which are different from that. So, we would look at a few high advanced bus clamping PWM schemes too here. and we would look at the analysis of that in the space vector domain. We would try to do a quick comparative analysis of a few PWM techniques, try to get a feel for the relative performance of the PWM techniques in terms of torque ripple, and we would also look at a couple of design examples for how you would design PWM methods for reducing the torque ripple, right. So, let us get started with the today's lecture. I would just call it as analysis of torque ripple in induction motor drives 2. The last lecture was 1. So, this is the second lecture and this would be the concluding lecture on the analysis of torque ripple. So, it is a usual 3 phase voltage source inverter and R, Y, B are the load terminals. You have connected the motor here and this is your DC bus and this is a DC bus midpoint. This DC bus midpoint is convenient for measurement of voltage at R, Y and B. So, you call it VRO, I mean you like then VRO is something we call as pole voltage, and VYO is Y phase pole voltage and VBO we call this as B phase pole voltage, and you subtract VRO and VYO you get VRY and so on and so forth. So, we looked at many of these and the PWM is about how do you generate the pulses for these 3 legs. Now, let us say these 3 legs are actually being switched at a very low frequency. So, this is some typical harmonic spectrum of a low frequency PWM method. So, let me indicate this is the magnitude of harmonic. So, what are the various frequency components there in the inverter output voltage? There is a fundamental component which is most important, which is what we want. Then this waveform, let us say, is presumably is having even half wave symmetry and therefore, there are no even harmonics now. So, there would be the third harmonic and the third harmonic is 0. The pole voltage might have third harmonic, but as I mentioned here this pole voltage might have third harmonic when you R with respect to O would have third harmonic, but when you subtract VRO minus VYO between VR and VY you will not have third harmonic. So, those third harmonics would get cancelled. So, there will be no third harmonic in the line voltage spectrum. Then you have the 5th harmonic, you will have 7th harmonic. Again your 9th would be absent because you are subtracting 2 pole voltages. Then this is 11, this is 13. So, this is 15 is absent. So, all the even harmonics are anyway absent. So, this is 17, this is 19 and so on, where this is the harmonic order n. So, let us say such a kind of a waveform is being applied whose frequency spectrum is like this. So, such a kind of frequency components are being applied onto that. So, the fundamental component gets applied on the motor, it is the one that produces the torque, essentially the steady torque. So, the current produced is can be calculated by this. This is the fundamental equivalent circuit. You want to analyze the effect of the fundamental voltage on the motor, you can use this equivalent circuit now. Other than the fundamental, there are harmonics. For analyzing the harmonics, you can use this harmonic equivalent circuit, where this LS and LR are the stator and the rotor leakage inductances, as we discussed in the previous class now. So, if your harmonic voltage is amplitude Vn, Vn upon n omega into Ls plus Lr would give you In, the harmonic, be the nth harmonic current amplitude. So, you have the 3 phase fundamental voltages. So, this considers only the fundamental component, let us say the component here, this considers only the component here. Let us go one by one. So, let us call that amplitude as Vm. So, it is Vm sin omega t minus 120, Vm sin omega t plus 120. So, what are these? These are the fundamental components of the 3 phase voltages that we have applied. Okay, so, they produce flux, they produce the fundamental flux. So, the relationship VR N1 is given like this now. This is the IR drop in the R phase winding. This RS is the stator resistance and this is the resistance drop in the stator winding, R phase stator winding, plus d psi R1 by dt. So, this is really the rate of change of flux linkage now, and as we discussed in the last class, this could be negligible in most cases, and you can say it is approximately equal to d psi R1 by dt. The same way Vyn, so you have d psi Y1 by dt, you have again Vbn1 is d psi B1 by dt. Now, the psi R1 is sinusoidal, therefore, d by dt of that would also be sinusoidal. So, it would be the amplitude of psi multiplied by frequency. So, that is what you will actually get here. So, I mean you will have this equation as I was mentioning the other day. This is from where you draw that V by F ratio to be constant. If the voltage and the frequency, the voltage to frequency ratio is held constant, then the amplitude would be constant. So, the fundamental one produces the fundamental flux. So, you have the 3 phase voltages, they are transformed into space vector, you have a vector of magnitude V 1 and you could think of a corresponding vector, that is the stator flux linkage vector. The magnitude of the stator flux linkage vector would be V 1 upon omega. So, and this is a vector which revolves like that, this is produces the fundamental magnetic field. Let us move on to the next. So, this is the fifth harmonic. As I told you the other day, this fifth harmonic, the sequence is now reversed, whereas for the fundamental, if you look at the sequences, it is omega t minus 120 and omega t plus 120, whereas for the fifth harmonic, it is omega t plus 120 and omega t minus 120, the sequence is reversed. So, as I mentioned before, and if the sequence is reversed, what happens? The magnetic field it produces is in the opposite direction. So, you all know that if you change the two terminals of an induction motor RYB, you swap two of those terminals, the motor will run in the opposite direction. Okay. So, this is what is VRN 5 does. So, it also produces magnetic field and those flux linkages are given by these equations now, right. So, this produces one. What is the frequency? This one let us call it psi phi and the psi phi would be V phi by phi omega. So, this is a revolving magnetic field, but it revolves at a frequency phi omega and in the opposite direction compared to omega. So, the relative speed between the fundamental magnetic field and the fifth harmonic magnetic field is 6 times the fundamental frequency, and this is why it leads to what is called a sixth harmonic torque. So, the fifth harmonic causes a fundamental vector like this, so psi s, whose magnitude can be given by that. Again it causes certain harmonic current which can be given by this now. So, where L is this leakage inductance now. So, this causes the fifth harmonic voltage causes certain fifth harmonic current and fifth harmonic flux. Alright. So, it is the same story about seventh harmonic, except that the seventh harmonic, as we saw the other day, it is the phase sequence is same as the fundamental, it is 7 omega t minus 120, then 7 omega t plus 120 or 7 omega t minus 240 or plus 120, whichever way. So, you see that the phase sequence is same as the fundamental voltages now. This also produces a magnetic field, this is also 3 phase voltage being applied to a 3 phase winding. So, it produces a revolving magnetic field, and in which direction is the same direction as the fundamental, because the sequence is same. Alright. So, what does it do? You can see this here, this is all illustrated. So, fundamental, this is the flux vector produced by the fundamental, this is the fifth harmonic, this is the seventh harmonic. Similarly, every other harmonic component 11, 13, 17, 19 would all produce magnetic fields, which we are not showing them here. Alright. So, let us move on to the next part. So, what happens because of that? So, the stator magnetic field revolves at fundamental frequency, this is we are trying to look at the fundamental component alone or simply the sinusoidal operation. So, the stator magnetic field produces revolves at the fundamental frequency, the rotor currents, there is some EMF induced in the rotor. So, that is at slip frequency. So, this MMF wave it goes past the rotor at slip frequency. So, slip frequency EMFs are induced in rotor and rotor provides a shorted path, and therefore, you are going to have slip frequency rotor currents. So, when you have slip frequency rotor currents, so the rotor is going to produce magnetic field, because its rotor is also like a 3 phase winding. So, it has currents flowing through that. So, there is it, and this magnetic field revolves at slip frequency with respect to the rotor. If the rotor magnetic field revolves at slip frequency with respect to the rotor, so with respect to the stator, it is the slip frequency plus the rotor zone frequency, which adds up to the synchronous frequency itself. So, the rotor magnetic field revolves at the fundamental frequency or synchronous frequency with respect to the stator. So, now you have two magnetic fields, one is the stator magnetic field and the other one is the rotor magnetic field. So, both of them are stationary with respect to one another, and that is the reason you are able to produce a steady torque, because torque is actually the cross product of these two magnetic fields. So, it depends on the strength of this magnetic field and the strength of the second magnetic field and the sign of the angle between the two. Since they are stationary with respect to each other, the angle between the two is constant and the sign of the angle between the two is constant, and therefore, the magnetic meaning the torque produced is constant. On the other hand, when you are looking at harmonics, when you look at magnetic fields of two different frequencies, then they will produce a pulsating torque, because the angle between the two fields is going on changing, and therefore, the torque will also go on changing now. This is what we will look at now. So, when you apply fifth harmonic voltage, it produces something revolving, that is at phi omega. Since it is in the opposite direction, we make it minus phi omega. So, the rotor is anyway rotating at omega r, therefore, it sees an MMF wave moves past the rotor at this frequency minus phi omega minus omega r, alright. So, frequency EMF, induced EMF in the rotor is of this frequency phi omega plus omega r. Such the rotor induced EMF is at this frequency phi omega plus omega r, therefore, the rotor induced currents are also at this frequency phi omega plus omega r. So, the rotor produces a magnetic field which revolves at this minus phi omega, I mean it is at phi omega plus omega r, but the the direction is reverse, and therefore, I have indicated a negative sign here now. So, this is how the rotor magnetic field is with respect to rotates with respect to the rotor, and with respect to the stator it is back to minus phi omega. So, what happens, you have the stator producing this 5th, 7th, 11th etc. applied on the stator. Consequently, there are magnetic fields of 5 like 5 omega, 7 omega, 11 omega, 13 omega etc. There are magnetic fields corresponding to the various components of the stator voltage, and these stator voltages in turn induce EMFs in the rotor and currents in the rotor, and they produce magnetic fields, and once again those are at frequencies omega, 5 omega, 7 omega, 11 omega, 13 omega. So, what we can say is the main torque is being produced by these two, that is what is revolving at omega and here what is revolving at omega. Any interaction between two here is pretty weak, because this magnetic field is not very strong, and let us say some magnetic field here, this is also not too strong. So, the interaction between these two is pretty small. So, what we need to consider is the interaction of these two fields which produces the fundamental torque, and the interaction between this field with any of these fields. Now, if you take this field which is revolving at omega and take this at minus phi omega, so the difference is 6 omega. So, there is an angle between this difference, and that actually varies at the 6th harmonic frequency. So, the angle between these two goes on changing in a cyclic fashion at 6 times the fundamental frequency. So, this fundamental magnetic field and the 5th harmonic magnetic field interact to produce 6th harmonic torque. The same way, the fundamental magnetic field and the 7th harmonic rotor magnetic field interact to produce the 6th harmonic torque. So, because again when you look at these two fields, the angle between these two fields changes, and it changes at the 6 times the fundamental frequency. The same way omega interacts with minus 11 omega to produce a 12th harmonic torque. This field interacts with this field to produce again a 12th harmonic torque. So, you can say that these are magnetic fields and they do this, and this is how the pulsating torques are actually getting produced, alright. So, now there are two magnetic fields. So, how do you represent a magnetic field? You can probably represent it in terms of flux or in terms of current. So, let us say we look at the stator magnetic field, the stator's fundamental magnetic field. So, we can look at the fundamental flux of the stator, and if you want to look at a harmonic magnetic field produced by one of the harmonic rotor harmonic currents, the harmonic fields of the rotor, then you can look at the harmonic currents. So, like I want to say an interaction between the fundamental magnetic field produced by the stator and one harmonic magnetic field produced by the rotor, I can possibly consider fundamental flux corresponding to the stator and a particular harmonic current corresponding to the rotor. So, I can look at this as an interaction between these two. We can also look at this as an interaction between fundamental current and harmonic fluxes, when you look at things from there, but the interaction between harmonic fluxes and harmonic currents is quite weak. So, what we would essentially say is we can actually look at what is the stator side fundamental flux or air gap flux, whichever way, and then you can look at currents, the rotor harmonic currents, and you can actually evaluate the 6th harmonic or the 12th harmonic pulsating torque. We did not go through the detailed procedures for this. So, this for interaction of fundamental with 5th and 7th produces 6th harmonic torque, and similarly 12th and all that, but as I mentioned to you, the details are available in these references. So, you could always look at these references where they tell you how exactly to calculate this based on the parameters, alright. So, this is a difference between the two. So, what happens here is you have your torque it is proportional to fundamental flux and it is proportional to the difference of these two currents, right. So, now this is fifth harmonic current, this itself is proportional to V 5 by 5, the fifth harmonic voltage divided by 5, and this is I 7 is V 7 by 7, because the fifth harmonic voltage sees 5 times the fundamental leakage reactance, the seventh harmonic voltage sees 7 times the fundamental leakage reactance. So, you have this as V 5 by 5, I V 7 by 7. So, what we saw towards the end of last lecture was that if we can actually eliminate V 5 by 5 minus V 7 by 7, or there is some phase relationship, but if you can actually work that out, and when you take them like what you call as V 5 and V 7 as cophasal, then you can say V 5 by 5 minus V 7 by 7 can be eliminated, you can possibly eliminate sixth harmonic torque. So, just as we could eliminate harmonic voltages. So, for the elimination of harmonic voltages we had considered the simplest case where we have 2 switching angles per quarter. So, you have 2 independent variables, with only one independent variable you can control only the fundamental voltage, with 2 angles you can control one fundamental voltage and one other harmonic voltage, and you could, so that controlling harmonic voltage means you could possibly eliminate that harmonic voltage, make it equal to 0, right. So, now you have your V 1 and this V 1 is 1 minus 2 cos alpha 1 plus 2 cos alpha 2 is V 1 star is one of the equation now. So, you want to choose your angles alpha 1 and alpha 2 such that your fundamental voltage is equal to desired fundamental voltage, let us say 0.8 per unit or 90% or 70%, something, this is the desired voltage that you want. So, this is one equation for you. The second equation, let us say you want to eliminate fifth harmonic voltage. So, it is 1 minus 2 cos phi alpha 1 plus 2 cos phi alpha 2 by 5, that is a fifth harmonic voltage, that should be equated to 0. So, by solving these two equations numerically, you will be able to find out some alpha 1 and alpha 2 which satisfy both these equations. So, you can get the desired fundamental voltage, you can also eliminate this. So, you can have 2 switching angles per quarter, you can obtain the desired fundamental voltage, eliminate one harmonic voltage. This is when you have 2 switching angles. In general, if you have k switching angles, you could get your desired fundamental voltage and it might be possible for you to eliminate up to k minus 1 harmonic voltages. So, that is selective harmonic elimination, selective elimination of harmonic voltages. Now, we are talking of selective elimination of harmonic torque. So, we want the fundamental voltage like before, V 1 is 1 minus 2 cos alpha 1 plus 2 cos alpha 2 equals V 1 star. But what we want is also that instead of the fundamental being particular harmonic voltage being eliminated, we want the particular harmonic torque to be eliminated. That can be achieved in certain cases by ensuring that V 5 by 5 minus V 7 by 7 is equal to 0. So, what is this V 5? It is 1 minus cos phi alpha 1 plus 2 cos phi alpha 2 divided by 5. And what is V 7? 1 minus 2 cos 7 alpha 1 plus 2 cos 7 alpha 2 the whole divided by 7. So, this V 5 by 5 minus V 7 by 7 you want to make it 0. So, you once again have two equations and 2 unknowns, you can solve them. But as some of you might recall from my lectures on low switching frequency PWM, selective harmonic PWM. So, you have 2 equations, 2 unknowns, it is not necessary that you should have a solution. In fact, you will not get solutions when you are very close to the 6 step operation, when your desired voltage is close to 1 per unit, where 1 per unit stands for the square wave fundamental voltage. So, like 0.95 to 1 per unit or so, there is some small range where you may not get any solution at all, and in some range you will get some solution, and there are also a few ranges where you would get multiple solutions. We have looked at all these, right. So, now this is just an example of selective elimination of harmonic torque with 2 switching angles, so that you can control the fundamental voltage and you can eliminate, let us say, the 6th harmonic torque. If you want, you can also eliminate the 12th harmonic torque. In general, what you do is you try to eliminate the harmonic torque which might come close to your resonant frequency. The system might have some resonant frequency. So, you will have a particular harmonic torque which might come close to that. So, one approach that engineers would use is actually to eliminate that particular torque now. So, to get a feel for this, we let us do a recap of what we did before. That is the switching angle plane, we had these 2 angles alpha 1 and alpha 2. So, these 2 angles alpha 1 and alpha 2, let us consider one of them along the x axis and another one along the y axis now. So, this is your plane. Now, you are looking at this plane, alpha 1 cannot exceed 90, alpha 2 cannot exceed 90 degree because it is within 1 quarter, and alpha 1 has to be less than alpha 2. So, you are essentially looking at this upper triangle, you are essentially looking at this upper triangle. So, this is the area within which you are looking at, all your possible PWM waveforms are within that now. So, if you are looking at V 1 is equal to 1 minus some particular fundamental voltage, let us say you consider this one. What is that line? This line is alpha 1 is equal to alpha 2. When you say alpha 1 is equal to alpha 2, you can see from this equation that it is 1. So, this corresponds to V 1 is equal to 1 per unit. So, it is a square wave operation, there is nothing more than that. If you want to take V 1 is equal to 0, you can see that this point would correspond to V 1 is equal to 0. You would find that this point alpha 1 is 16, alpha 2 equals 90 also corresponds to, you can put these numbers in C. We have done this all in good detail earlier. So, actually you will get a set of all points like this. Along this line you will get V 1 is equal to 0. What does it mean? You are producing a PWM waveform which has two switching angles as shown here, but the fundamental voltage is 0. So, it is not unique, there are several pairs of switching angles available for you, each of these pair can actually give you V 1 is equal to 0. So, let us say you want V 1 is equal to 0.2 per unit or so, you will get some other curve like this, you might get some other curve like this. If you want to look at V 1 is equal to 0.5 or so, you might get some other curve which may be like this, and we want something like V 1 is equal to 0.8 per unit or so, you may get some other curve like this. So, these are all different values of V 1. So, these are what we can call as constant fundamental voltage contours on this alpha 1 versus alpha 2 plane. Now, we are interested in seeing the harmonics. So, now there are so many options for you, that is if you want a particular value of V 1, let us say this is V 1 is equal to 0.2 per unit, you can use any of these points here along this curve. Which point do you use? It depends on which one to choose, that depends on your criteria for selection. Now, let us say you want your criteria for selection is that fifth harmonic should not exist. So, you want to see where fifth harmonic is. So, it is actually possible to plot the fifth harmonic currents also here, I mean the wait a minute, yeah. So, we can see where all fifth harmonic is 0, that is you can consider this equation, and based on this equation like you can look at several values of alpha 1 and alpha 2 which would satisfy this equation V 5 is equal to 0. So, if you try this, you can plot this, we have also done this before, in case you have not done this it is a nice exercise for you to do it. So, you would actually get certain angles like this, you would actually get a curve like this. This is but not the only ones, here also you will get a curve like this, this is within this range, this actually is a part of a larger curve, again this is also part of a larger curve. This curve can be obtained by shifting this contour by 72 degrees and shifting further up by 72 degrees. This 72 degrees is 360 by 5 which is really the fifth harmonic frequency. Now, you can also look at where there are the seventh harmonic components are there. So, I can consider this equation and you can equate this to 0 and you can see the set of all points where seventh harmonic is 0. You will once again see that this point seventh harmonic is 0, you will see that at this point seventh harmonic is 0. So, those are actually the points at which the PWM waveform is a triplen in frequency square wave, it is a third frequency square wave. So, you will not have any components other than the third harmonics there. So, if you look at that, this sixth harmonic there will be another fellow here, you may have it as like this, yeah, you may have some V 7 is equal to 0 curve here, you may have another V 7 is equal to 0 curve which is going up, which is not within our interest, and you will have another V 7 is equal to 0 curve like this, you may have some other curve like this. So, we have done this all before, we are just trying to do this as a recap. So, these are also constant voltage contours, but while these are constant fundamental voltage contours, these are constant harmonic voltage contours. This green line is for example V 5 is equal to 0, this line is V 7 is equal to 0. So, now if you choose this point for example, you get at this fundamental voltage you will get your fifth harmonic to be 0. So, you choose this point, you are going to get seventh harmonic to be 0. So, it is possible for you to eliminate. So, depending on where you choose, like here or here, you can actually operate with 0 fundamental fifth harmonic or 0 seventh harmonic. Similarly, it is also possible to look at where 11th harmonic is 0, where 13th harmonic is 0. It is also possible to look at certain combinations of harmonics and see, square root of V5 square plus V7 square is low. Many times what is done is the weighted THD of voltage is considered to be low, that is also done at times now. So, now what are we trying to do? We are trying to look at the sixth harmonic torque to be eliminated. So, let me quickly reproduce some of these curves here. So, you want, this is your V5 is equal to 0. Now, you have V7 is equal to 0. This is like this. So, obviously, there is a point here where both V5 or V7 is equal to 0. So, at that point there is some modulation index, at that modulation index you are able to eliminate both fifth and seventh harmonic, but you can't do it everywhere, it is only there. But at that point your sixth harmonic is 0, which is a particular case V5 by 5 where V5 is 0 and V7 is also 0. So, you have this point. Now, what you can do is there you can actually look at set of all points where that is 0. So, you would actually find that maybe there are a few points like this, there are a few points like this. You solve for this equation. One way to do this, maybe you say alpha 1 is equal to 0 and then try to find out the different possible values of alpha 2, or you can consider some other value. So, you can do this. So, you will also find that the sixth harmonic torque is 0 there, because once again you have V5 as well as V7 going 0 there. And the same way, if I redraw that curve, I have this fifth harmonic curve and I would have another seventh harmonic being 0 like this. This is again a point at which I will have the sixth harmonic is 0. So, these are 3 points where I have sixth harmonic to be 0, but these 2 points are actually on your V1 is equal to 0 line. These are on your V1 is equal to 0 line. So, you have these points, but you will also get some points in the neighborhood. You will get a few points in the neighborhood certainly, which satisfies this V5 by 5 minus V7 by 7. I would certainly encourage you to solve this and try. So, these are all some points where you get. So, you get some feel for what can be done and how things can be done and so on and so forth. So, this is about how you can eliminate that. It is a very simple exercise, but it is to enhance our own understanding of how things change and how it works and how you can eliminate harmonic torques. So, you can generalize it. So, this is I have looked at only one switching angle. If you have multiple switching angles, just you can have like as you can eliminate multiple harmonic voltages, it may be possible for you to eliminate multiple harmonic torques also. But all said and done, if you can eliminate multiple harmonics, you could also eliminate multiple torques. For example, if you have 3 switching angles per quarter, you control your fundamental voltage and eliminate both V5 and V7. So, you are ensuring V5 is equal to 0 and V7 is equal to 0, sixth is automatically gone. So, similarly, if you have let us say about 9 switching angles, you can control your fundamental voltage and 4 pairs of harmonics can be eliminated. So, many times when they eliminate harmonic voltages, they will eliminate in pairs, because that makes sure that a particular torque component does not exist. If you eliminate fundamental and the first 4 pairs of harmonics like 5 and 7, 11 and 13, 15 and 17 and 19 and 23 and 24, 23 and 25, you are ensuring that there is no 6th harmonic torque, 12th harmonic torque, 18th harmonic torque and 24th harmonic torque. So, that is normally what is also done. So, you can eliminate the harmonic voltages. Once you eliminate a pair of harmonic voltages, it is the particular harmonic current is gone. So, now we are going to look at the high switching frequency part, like it is this is when you go to high switching frequency, the pulsating torque is not going to be as bad as it is in the low frequency, but still it is good to develop a good understanding of this. So, you have this triangle comparison or this space vector based approach where you have this. So, what happens in these cases is there is a volt second balance. The triangle comparison method goes on a phase by phase basis. For every phase it says I need so much of average voltage, and that much of average voltage is actually applied by the inverter. So, the applied voltage and the reference voltage or commanded voltage are equal over every sub cycle or every half carrier cycle, and that is what you call as volt second balance. Here the voltage reference is not provided in terms of 3 phase voltages, it is provided as one reference vector. So, the inverter applies an average voltage vector equal to the reference vector. So, the applied vector is equal to the reference vector, and once again you call it volt second balance. Therefore, this is how you do that, and this volt second balance is maintained over small intervals of time which is called sub cycle. A sub cycle could be like, if your fundamental cycle is 50 hertz, your sub cycle could be as low as like 100 microsecond or 50 microsecond, depends on your switching frequency, how high you are switching now. So, yeah, like there are some ranges like 15 to 20 times the fundamental or so, where you can have significant pulsating torque, and that is where these kind of exercises can actually help you reduce the pulsating torque here. So, let us say this volt second balance, what is the problem? There is an instantaneous error between the applied voltage and the reference voltage. You are matching them in on an average sense, but not in an instantaneous sense. Therefore, there is a difference between the two, and that is what causes ripple current, and the same is the cause for pulsating torque also. We used this for the analysis of ripple current before, and we are going to use the same thing for analyzing the torque ripple now, right. So, let us say this is your vector, this is your space vector plane, and you have your fundamental reference going around that. So, you are now looking at sector 1. So, if you are going to apply that reference vector, what do? You apply your active vector for t1 seconds and this active vector 2 for t2 seconds and the null vector for the remaining time. So, that you have this voltage like this. So, what produces is here. So, this reference vector is produced now by applying this for t1 seconds and this for t2 seconds and t is the null vector for the remaining ones. And how are they calculated? This is what is volt second balance. This is the reference volt second, this is the applied volt second, they are equal, and the subcycle time is equal to the active vector time 1, active vector 2 times, and the null vector time. And T1 is calculated based on your magnitude and angle of the reference vector. T2 is also calculated based on the magnitude and angle, and Tz is Ts minus T1 minus T2. So, we did this in good detail when we did the module on space vector based PWM. Now, you can produce this in many sequences. What is normally done is your conventional switching sequence, that is you start from here and you go there, that is you apply this for Tz by 2 seconds, you apply active vector for T1 seconds, you do this for T2 seconds, and then you once again come here and do it for Tz by 2 seconds. But now this is what is called as clamping sequence. You do not have to go to the null vector twice, you can apply this null vector for entire Tz seconds here itself. You can stay at minus 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 for Tz seconds, then switch your R phase, so that you go to plus minus minus. You stay here for T1 seconds, then switch your Y phase, so that you go to active vector 2 and stay there for T2 seconds. Your subcycle is over. Next subcycle, what do? Stay here for T2 seconds, then switch your Y phase, come to active vector 1, stay here for T1 seconds, and then you switch your R phase and return back to minus minus minus. So, what happens is here B phase is never switched and it is clamped. You can see B is negative here, B is negative here, B is also negative here. B phase is clamped to the negative DC bus, and so we call it as a clamping sequence, and this is clamping sequence 1, clamping sequence 1, where a phase gets clamped to the negative bus. There can be another clamping sequence. For example, you can avoid this 0 state 0 fully. Let us say you start from your active vector 1, apply this for T1 seconds, switch your Y phase and move here. Apply this vector for T2 seconds, then switch your B phase and move here, stay here for Tz seconds. Your subcycle is complete, you have produces this reference vector. In the next subcycle, you will have to produce another reference vector which will be close to this and different by certain angle. So, what do? You start from this 0 vector time, stay here for Tz seconds, switch your B phase, come to T2, switch your Y phase and come to 1 and stay here for T1 seconds. So, we can call this as clamping sequence 2. It is clamping because you see that minus 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 is never used, and R phase is always positive here and also positive here. R phase is clamped to the positive bus. So, this is a clamping sequence. To distinguish between those two, we call as clamping sequence 1 and this is clamping sequence 2. So, what you can actually do is these are two popular PWM methods. This is one kind of clamping. So, you use this within your sector 1, you use this 7 to 1 in the first half and 0 1 2 in the second half, and you use similar sequences in the rest of sector. And you will see that your R phase is clamped here to the positive bus, because 7 is plus 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 and minus 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 is never used here. R phase is clamped to the positive bus here. So, R phase will be clamped to the negative bus here. So, every phase will be clamped to one of the DC rails in the middle 60-degree duration of its of its fundamental cycle. Now, if you look at here, this is a place where R phase is clamped when 761 is applied. Again, this is a place when 7121 is applied, R phase is clamped to the positive bus, and R phase has a positive 0 crossing here. This is 0 degree, this is 30, this is 60. So, between 30 to 60, R phase is clamped to the positive bus. This is 90, this is 120, this is 150. This is 120 to 150, once again R phase is clamped to the positive bus. So, R phase is clamped to the positive bus during the middle 30-degree duration of this quarter cycle, again the middle 30-degree duration of that quarter cycle. So, we call this as 60-degree clamp PWM method and 30-degree clamp PWM method. Now, there are variations. This is where space vector based PWM is a little different. You can apply one of the active vectors twice. We saw an example earlier where you can apply 0 and go to 1, do not stay for t1 seconds, stay only for t1 by 2. Go here, stay for t2 seconds and come back here and finally spend t1 seconds, that is 0, 1, 2, 1. We saw this example when we did the space vector based PWM module, and we also when we did the analysis of line current ripple. Now, there is another variation we are just looking at here. Let us say we start from 1, we are here. So, we are not going to be here for the entire t1 seconds, but we are here for t1 by 2 seconds, half of what is required. Then switch this phase, which phase is that? R phase. Go here, stay here for tz seconds, then come back to active vector 1, stay here for the remaining t1 by 2 seconds, then switch y phase, go here and stay here for t2 seconds. So, one subcycle is complete and you have applied the null vector for tz second and this one for t1 seconds and this two for t2 seconds. So, you are going to produce the desired reference vector, no doubt, except that you are applying the voltage vectors in different sequences now. What you are doing is also you are switching R phase twice, you are switching Y phase once and you are not switching B phase at all. You may worried that what happens to the balance, there are some phases getting switched more. What you will do is in a different sector, we are talking of sector 1 or in a different sector or maybe in a different part of sector 1 itself, we may double switch another phase and may clamp R phase. So, everything will get balanced. If you employ the switching sequences in a symmetric fashion, all that problem will be sorted out. So, you can see that it is 1 0 1 2. So, this is an example. So, you have gone here, the next subcycle what do? You stay here for t2 seconds and switch your y phase, come here, stay here for t1 by 2 seconds, go here, stay here for tz seconds and come back and stay here for t1 by 2 seconds, your subcycle is over. So, it is 1 0 1 2 2 1 0 1 1 0 1 2 2, you can go on like that when your reference vector is moving through sector 1. The same way you can also look at 2 7 2 1, that is what is illustrated here. You stay here for t2 by 2 seconds, go here, stay for tz seconds, go back and spend t2 by 2 seconds here and go here and stay here for t1 seconds. So, you are going to get the same reference vector, but now the sequence is 2 7 2 1 and you can also do 1 2 7 2 in the next subcycle. So, you can use these two sequences in alternate subcycles. So, you have these special sequences which switches twice. You can see that in a half carrier cycle a phase can switch only once in triangle comparison based PWM, because it can only intersect once, whereas here you can see it is switching twice. So, this is a benefit that we are getting. We are able to divide an active vector time. What we are doing is this active vector is applied twice, which is not possible normally in methods like sine triangle PWM, etc. So, an active state will be only applied once. So, the only option is between the two 0 states, either both will be applied or one will be applied. If both are applied, again one may be applied for 0.8 tz, other one may be applied for 0.2 tz or whatever. So, there the only degree of freedom is division of null vector time between the two 0 states. Here you have that freedom. So, you are actually using only t7 sometime, or you are using only the 0 state 0 sometime. Apart from that, you are using this active state division time, which is actually a freedom that is available with space vector PWM methods. So, you can employ the sequence 1 0 1 2 2 1 0 1 in the first half, 2 7 2 1 1 2 7 2 etc. in the second half, and similar sequences in the other sectors. So, this is one example of an advanced bus clamping PWM scheme. You can think of various such advanced bus clamping PWM schemes. Quite a few of them have been reported in the literature recently. So, what happens now? We are now going to analyze the error. So, this is the error. When you have applied reference vector, what you want is the reference vector, but you have applied a null vector. So, the error is this V error vector. Again, what you want is this vector, you have applied V1 vector. So, this is your error vector. Again, sometime what you want is this reference vector, what you have applied is V2 vector. So, this is your error vector. So, when you want this reference vector, sometimes you have an error like this, you have an error like this, or sometimes you have an error like this, and this error is a problem. What does this error represent? This error represents all your harmonic voltages in a per phase, all the harmonic voltages, add them up, you get a ripple voltage. So, those 3 phase ripple voltages, you transform them into the space vector domain, that is this error voltage. What is this Vref vector? You have the 3 phase fundamental voltages, transform them into the space vector domain, and that is your Vref. Is it okay? So, now what happens with the switching sequence? You may generate the same reference voltage vector, but the voltage vector is applied in different sequence. Therefore, the error, that is the applied vector minus the reference vector, is different. So, the instantaneous applied voltage vector differs with switching sequence. Therefore, the instantaneous error voltage vector differs with switching sequence, and therefore, the stator flux ripple vector or current ripple vector differs now. So, what is that error voltage vector? It is, after all, it is a representative of the various harmonics. So, the harmonics see the motor as its leakage inductance. So, you can simply integrate this error voltage vector to get a measure of the current ripple, and that is what you call as the stator flux ripple vector, which is actually a measure of current ripple. So, the stator flux ripple vector or the current ripple vector is actually different for different sequences, because the instantaneous error voltage vector is different. That is different because the instantaneous applied voltage vector is different. So, this is different when the sequence in which the vectors are applied is different. This is how the switching sequence is influenced. So, this is a quick illustration of what happens here now. So, you have this reference vector, Now, what we have done is, this is a plane, we will take this axis as q axis and we will consider this axis as the d axis. So, d axis is where your fundamental flux vector is, and this is q axis, your applied voltage vector. At the start of the subcycle you are here, then you are integrating the error voltage vector. So, when you are integrating the error voltage vector moves like this. After that, the error voltage vector starts moving like this, is, let us say, what you call as the error or the stator flux vector. When active vector 1 is applied, you have this line, it moves parallel to this line. This is when active vector 1 is applied. And when it is switched from active vector 2, the error voltage vector changes, and therefore, the integral of error voltage vector or the stator flux ripple vector also changes, and it moves along this line. Its tip moves along this line, and finally, it comes here and it switches here, and this is where 7. So, it starts from 0 magnitude, its magnitude goes on increasing in this direction, then its tip moves along this direction, it reaches here, again the tip moves back, and finally here it goes back to 0. That is because volt second balance has been maintained. The error voltage vector averaged over a subcycle is actually, it is 0. So, it starts from error, the integral of the error voltage vector starts from 0, ends in 0. So, this is what happens when you apply 0, 1, 2, 7, right. So, the only difference that we are going to look at here is, see what causes this ripple. There is something on the q axis, there is something along the d axis. So, you can actually resolve this error along the q axis, error along the d axis, and you can compute the RMS along the d axis, RMS along the q axis, and then you get the overall RMS. This is what we did when we analyzed the current ripple. Now, we want the torque ripple. What is this torque ripple? Like pulsating torque. So, you are actually looking at the harmonics interacting with the fundamental flux. Your fundamental flux is along the d axis. So, you are looking at the pulsating fields which are perpendicular to that. These are basically caused by these harmonic currents, and it is your q axis ripple that is actually going to give you torque ripple. So, any ripple along the d axis is not going to, because your steady flux is along this direction. So, this is not going to interact. If you consider the ripple along d axis, there is no cross product. So, you need some cross product, whereas, so your fundamental flux being or steady flux being along d axis, any ripple along q axis would actually cause you the pulsating torque. So, when the difference is, you have to consider only this, that is, you start from 0, the q axis ripple goes to a maximum, and after this what happens? The q axis ripple is coming down, here it is 0, here it is going to negative, here it is going to some negative maximum, or it is a positive maximum, here it is negative maximum, and then here crosses 0 and goes to positive maximum, and then again it slightly slowly reduces, goes down here, and from here it reduces fast and goes back to 0. So, this way of the psi q, if you take, that is a measure of your torque ripple, and you can compute the RMS value of the torque ripple. Now, if you change your sequence to something else, for example, from your conventional sequence you go to some other sequence, you see that the origin has been shifted here. That is, you may look at this is your psi vector, whereas here this is your psi vector. these two triangles are almost the same, except that you look at this point, it has been shifted. Why that is being shifted? Here it is equal, here it is not. So, this is the effect of common mode addition. So, here you have added common mode such that the active vector times the null vector times are divided equally. So, this is a measure of your null vector time, this is again a measure of your null vector time. Here this is like T 0 and this is T 7, here T 0 is longer than T 7. So, you have this now. So, what happens? You can see your q axis flux ripple, it is some negative maximum, it is some positive maximum, whereas here you can see your negative maximum is much higher than what you have here. So, in this case you will have lower q axis ripple, in this case you have higher amount of q axis ripple, and therefore, this is going to lead you to more amount of pulsating torque. Therefore, if you divide the null vector time equally, your pulsating torque is low, if you divide it unequally, in general your pulsating torque is higher. So, dividing it equally is not actually optimal, it is suboptimal, but it is very close to what is optimal. Many a times when you are using continuous PWM, it is best that you divide that equally. If you divide that, what happens? The q axis current ripple reduces, therefore, the torque ripple reduces, of course, the overall current ripple also reduces now. So, this is one comparison. So, conventional space vector PWM is better than sine triangle PWM and third harmonic injection except 1/4. Third harmonic injection 1/4 is similar to conventional space vector. So, it is better than those PWM methods now. So, if you use 0, 1, 2, 1 for example, what is happening is you have this is when 0 is applied, this is when 1 is applied, this is when 2 is applied, this is when 7 is applied. So, this is your flux ripple vector or current ripple vector trajectory. Now, if you are going to do it as 0 1 2 1, I am sorry, the d axis must be here, ignore this. So, when it is 0, it goes like this, and when you apply 1, it goes like this. When you apply 2, the tip goes like this, when you apply 1, it goes like this. So, we had also done this when we were analyzing the current ripple. There are quite a few papers which discuss these things in good detail now. So, here what you can see is you look at your peak d axis ripple, you see your peak d axis ripple, here you see your peak d axis ripple. Your peak d axis ripple is much lower here, whereas your peak d axis ripple is much higher here. So, you are able to reduce your d axis ripple, this means a considerable reduction in your current ripple, though not necessarily in torque ripple. You have another example of, let us say 0 1 2 7. Now, I am considered a different value of reference vector, this is 0 1 2 and 7. So, the flux vector actually tip moves along this path. So, if you compare this with something else like 0, the same picture I have reproduced here 0 1 2 7, I am comparing this with 1 0 1 2, this is let us say 1, this is 0 0, it continues, this is 1, this is 2. So, when I apply it in a different sequence as I show here, you see that this is like a triangular one, you see that it is doubly triangular. Now, sometimes it is possible that this is my peak q axis, here it is my peak q axis ripple. It is possible that my peak q axis ripple is lower than that, or the RMS q axis ripple here could be lower than this if you choose it correctly. For certain values of Vref, this could be better. You have to find out what those values are. So, that is what has been done in the literature to come up with improved PWM methods now. So, to actually calculate the RMS stator flux ripple along the d axis and q axis, so this is a useful reference. What you need to do is you have to resolve this along q axis and then d axis, you will get piecewise linear functions, you have to calculate square and calculate the area under them. So, this has actually been, I have also mentioned this reference earlier to you when doing the line current ripple module, right. So, you will actually get this as one function, this is the q axis ripple, you will get it as some function of Vref alpha and Ts, and you will get the total stator flux ripple also as some function of Vref alpha and Ts, and the nature of the function is actually shown. So, what you can do is this is available, this will be a different function, this coefficients will be different for different sequences, it will be something for conventional, it will be something for 0 1 2 1, something else for 1 0 1 2, etc. It is possible for you to compute all this and compare them, and once you compare them, it is easy for you to generate many PWM methods. For example, you take your sector 1, this is your active vector 1, this is your active vector 2. Now, what you will see is you will have a range of vectors, that is you may have a vector whose tip is like this. If there is a vector whose tip is like this, then you can apply 0 1 2. 0 1 2 will give you lower q axis ripple than 0 1 2 1, 0 1 2 7. Similarly, you may have another one, you may have another region like this. If you have, if your reference vector tip falls within this region, then 7 to 1 could be better, means it could give you lower flux q axis ripple than 0 1 2 7, and in this region 0 1 2 7 can be better. So, depending on where your reference vector falls, you can either choose 0 1 2 7 or 0 1 2 or 7 to 1. The same thing you can do in all the other sectors. So, this can actually reduce the torque ripple for you. Similarly, let us say if you have 0 1 2 7 etc., any sequences can be combined. What you will find is, if you do an analysis, you go by the current ripple, you will find that there is a particular area where 1012 gives lower current ripple than the others. Again you will find some area where 2721 gives lower current ripple than the others, and 0127 gives a lower current ripple than the others. Now you can use a combination of these three sequences. Whenever the reference vector falls here, you use this sequence. Whenever it falls here, you use this sequence. When it falls here, you do this. Now this will give you a slightly lower current ripple and a significantly lower torque ripple. It reduces the q axis. These two sequences reduce the q axis ripple compared to 0 1 2 7 in these regions. Now, so this is how you design the hybrid PWM methods. These are all discussed in good detail in these two papers. The first one is the earlier method, which is a combination of the conventional and the clamping sequences, and the second one is the second method that I indicated. So you can see these two methods in good detail in these two papers. So these are some other references where the d axis and the q axis, what are their significances, these kind of things are explained here. There is also an earlier paper by Professor Fukuda which talks about these things. So this is one paper where you talk of the d axis and the q axis ripple and their significances, and this is another one interesting paper where this PWM method, where you use 1012 and 2721, it reduces the motor acoustic noise. It is not on pulsating torque, but it shows that this kind of a sequence has the benefit of reducing the acoustic noise. So you can go through these references for further knowledge in this, and I thank you very much for your attention, and I hope you were benefited by this lecture, and hope you would continue to have interest in the subsequent lectures. Thank you very much.